Welcome to Selected Advanced Math for High School. Today we'll discuss matrix multiplication. Maybe some of you have already been introduced to this, and many of you have the question, why is matrix multiplication defined the way they are? So today we'll explore this question. It's a very important topic, and our discussion will happen in the context of two dimensions. So the most natural way to talk about matrices, we really need to introduce vectors. So today our discussion, we will focus on two-dimensional vectors. And so the best way to describe two-dimensional vectors is to draw a coordinate system like this, which has an origin 0, 0. And a vector is a directed line segment from 0, 0 to a point A. So if A is the coordinate, X and Y are the coordinates of the point A, then OA is a vector, and we represent it by just writing the X and Y coordinates as a column vector. So this is kind of definition of a column vector also. Basically, you just write it like this. So this is your vector. So the vector OA is represented by a column like this with X as the X coordinate of the point A and Y is the Y coordinate of the point, of the same point. Now, so every point in a plane corresponds to a vector. It's called two-dimensional vector, and we will not discuss why it is two-dimensional. That we'll have the discussion for another day. But to begin with, let's get examples, lots of examples. So, for example, this is called the zero vector. Okay, so it goes from, so it is the arrow connecting 0, 0 to 0, 0. Makes sense, right? Now, okay, let's take another example. So, for example, 1, 0 is the vector connecting 0, 0 with 1, 0. So let's draw that with another color. So it's connecting from here, and let's say this is the point 1, 0. So here you have a vector. I'm just drawing it slightly below just to distinguish, but actually it's lying on that x-axis. So this is the vector 1, 0. Okay. Now in the next slide, we'll see that vectors can be added. Just like numbers, vectors can be added, and let's see that. So again, take an example. let's take two vectors. Let's call it, what should we call it? 1, 2, and maybe let's call it another 1, 1. Okay. So what are these two vectors? Let's draw the line again. Okay, so let's this be 1, this be 2, 1, 2. Okay. So the vector 1, 2 is the point here. This is the vector. This is the vector 1, 2. What about the vector 1, 1? 1, 1 is right here. So let's draw with another color. So 1, 1 is the vector here. So I've got two vectors here. Now, the addition of these two vectors, the addition of these two vectors is by the following rule. So you get 1, 2, you're adding 1, 1. Basically, you just add the x coordinates and add the y coordinates. So this is 1 plus 1, 2 plus 1. So this is 1, 3. So let's find the point 1, 3 with another color. So the point 1, 3 will be somewhere here because this is 3. So 1, 3 should be somewhere. I'm sorry, this is 2, 3. Yeah. So that is a mistake. Let's correct that. This is not 1, but this is actually 2. So the point 2, 3. The point 2, 3 is somewhere here, and you draw the line to this point 2, 3. Okay. So this is the definition of adding two vectors, and you can check it that this is the same as completing a parallelogram here in the following way. So let's complete the parallelogram. If you complete this parallelogram with these at the sides, then this is the diagonal of this parallelogram. But bottom line is that we know how to adding two vectors. So let's say we take two vectors x1, y1 and x2, y2, and this addition is defined as x1 plus x2, y1 plus y2. We just saw an example of that. Now notice that 0, 0 vector has the property that if you add it to any vector, so let's say we add it to a vector called 595. So then this will be 0 plus 5, 0 plus 95. So that's 5195. And in general, as you can see, 0, 0, if you add to any vector xy, you will get the same vector xy. So not only you can add two vectors, you also have a notion of a zero vector. If you add that zero vector to any other vector, you get the same vector back, just like the number 0 uh, in real numbers. Okay. In the same way, for every vector x and y, for every vector x and y, we have a negative of that vector. Okay, has a negative of the vector. So what's the negative of xy? Negative of x and y is minus x minus y. Now, why do we call it a negative? Because if we add these two, you'll get 0. Notice that xy plus minus x minus y equal to x minus x, y minus y equal to the 0 vector. Okay, So we have a zero vector. We can add any two vectors. And we just saw that for every vector, we have its negative. So should we say 1, 2, 3, for every vector, we have a negative vector. So xy, and then the negative vector is minus x minus y. And vector plus its negative gives you a zero vector. Okay, last thing I want to say that we can multiply a vector, let's say 5 by 5, 3, by a number. So for example, if we multiply 5, 3 by the number 3 by 5, then we get the vector. So you can write 3 by 5 times 5, 3. You just multiply all the components. So this is 3 by 5 times 5, 3 by 5 times 3. So you get whatever you get. You get 3 over 9 by 5. That's not important. What is important is that if you have a, so in the same spirit, if you have a number a, multiplying by the vector xy gives you the vector by definition ax, ay. So actually, this is what we call, this is known as definition of a vector space. So the set of all such vectors which can be added, there is a 0 and you can multiply with a number, is called a vector space. So the two-dimensional plane can be thought of as a two-dimensional vector space. Okay, so now we are getting ready to talk about matrices. You might be wondering, why have we not talked about matrix at all and only talking about vectors? That's because now we are going to introduce a very important concept, a map from vectors in a plane to another vector. So let me give an example. Suppose we say that we take an arbitrary vector. Arbitrary means no particularly special one. So when an arbitrary vector, we always define an arbitrary vector as having x, y, where x and y are variables. So suppose I give a rule. We give a rule. So we call this rule of mapping or transformation rule. By that I mean you have the vector given xy, we map this to a vector, you can just say x plus 1, y plus 1. So this is the simplest thing. So actually, probably this is not the simplest thing. Let me give another example. So let's erase that one. Let's say we'll erase this, and okay. So I'll map this to a vector. Let's say with the new components, which is x becomes x plus y and y remains y. So let's see geometrically what's happening. Take an example. Okay. The vector 1 1 goes to gets mapped to 1 plus 1 1, which is 2 1. And similarly for any vector, for example, so if you just draw this, which is 1 1, so 1 1 is this vector, and then we associate that by some miracle. Somebody tells you that it is associated with we transform it to this vector. We just map it. Okay. So you see, so let's write down the most critical thing. We are mapping each vector to another vector. Okay, that's all we are doing. So let's take another example of a mapping, another mapping. Suppose you start to xy gets mapped to x0. So you can say, if you take a picture, so if you have a picture like xy, so this is the point xy, then the new vector is, the projected vector is here. The projected vector is x0. So you can see this is a projection. So now we'll see how to neatly describe this mapping. So again, take an example. Take a map, or it is called also a transformation because it transforms one vector to another. Transformation. Let's take the same example. Xy goes to, this arrow means we are taking xy and getting a new vector called x plus y and y. Now notice that the new x and y, the new x is x plus y, the new y is old y, that's okay, doesn't have to be, but these are linear expressions involving x and y, and these are called linear transformations. So let me give an example of x and y going to x square y. This is not a linear transformation. Okay, so let's stick to this example. Again, stick to the example. Take xy goes to x plus y, and y I will write it as 0 plus y. Now, the most important thing, we write this transformation as if we have these coefficients is here 1, these coefficients 1, this is 0. So we'll write that x plus y is equal to, just take the coefficients of x and y, 1 1 0 1 xy. So this is just a way to remember that this is the map. Okay. So, or you can write in a standard way 1 1 0 1 xy. This 0 should be a little further to the left. So this is equal to this transform that silly thing that we wrote down 0 1, sorry 1 1 0 1. We'll call it soon. But the rule is this is 1 times x plus 1 times y, 0 times x plus 1 times y, which is x plus y, y. So basically what we're doing, we are writing the transformation xy going to x plus y, y as just taking the coefficients of x and y, the linear coefficients, and just putting this here as and saying this is equal to x plus y, y. So this defines this matrix, defines this matrix, defines this object. We'll call this matrix, which we'll call a matrix. And it's called, it has two rows, two rows. So one row is 1 1, the other row is 0 1. This is the first row. This is the second row. And two columns. So one column is 1 0, second column is 1 1. This is the reason why this is called a 2 by 2 matrix. Two rows and two columns. Okay, so now notice that we have not talked about matrix multiplication at all. This is just the notation that we're using to remember what is the transformation. So let's take another example. Okay, so suppose our rule of transformation was the following: xy going to xy. So basically it doesn't change. So what is the corresponding matrix? So you notice that this xy equal to 1 times x plus 0 times y, and this is 0 times x plus 1 times y. So the matrix is 1 0 0 1 xy equal to the transform matrix xy. Let's take another example. So let's take another example. Let's say xy goes to x0. This is called projection. So how do you represent the 2 by 2 matrix? So remember again, this xy is nothing but 1 times x plus 0 times y. There is no y here. And here it is 0 times x plus 0 times y. So the matrix is obviously 1 0. Okay, so I got 1, I got 0, and the next row 0 0, and it operates on xy and produce x0. Okay, so this is the definition of the matrix, and we just told you how to get, what's the rule to get the new transformed vector. All right, so now one more thing I want to talk about is that so every linear transformations of vectors in 2 dimension to another vector in 2 dimension is equivalent to a matrix transformation. So given a matrix, for example, let's say 5, 3, 2, minus 1. How does it act on x and y? What's the new transform vector? It's simple. 5 times x plus 3 times y, 2 times x minus 1 times y. That's it. So you've got your new vector xy becomes 5x plus 3y, 2x minus y. Perfectly good transformation. Okay, so now we are about to talk about matrix multiplication. Let's see how it happens. So suppose we have a transformation okay. So the vectors in, so we call this vector v to v. This is a transformation v to v. Example, again, xy goes to x plus y, y. So let's say this is a matrix here, which we'll call some matrix. So in this case, the matrix is what? Matrix is 1, 1, 0, 1. So that all that it means is that under this transformation, 1, 1, 0, 1 acting on xy vector gives you the vector which is x plus y, y. But suppose I do a second transformation. So I got this, and now I will act on it and another transformation. Well, let's say that I transform it with a matrix like, let's say 1, 0, 1, 1. So what does this one do? This one takes a, so we had a xy here, and that came here, became x plus y, y. Now this one, it takes this, and what does it do? So take a vector xy here. So this vector will give you one times x plus 0 times y, 1 times x plus 1 times y. So this gives you x, x plus y. Okay. But suppose now you want to combine these two. So far I acted a vector from here, and then forgetting about this, I had another transformation like that. But suppose I want to compose the two together. So I transform first by, so my x and y goes to x plus y, y, and that will now go to x plus y, x plus y plus y, which is x plus 2y. So now notice that I have a transformation from here to here. What is that vector here? That vector is, that matrix is 1, 1, 1, 2. So what we are doing, we are transforming, first taking the vector, transforming by this vector, and then we are multiplying, we are transposing again with this vector 1, 0, 1, 1. And final transformation is this. So these two must combine in such a way that I get back this. Okay. And so let us take a general example. So now it is important to take a general example. So let's say we have taken a vector V with a matrix A, and then I'm applying again a matrix B. So matrix A is, we'll write this down as A11, A12, A21, A2. So this is the first row. This is the second row. And similarly, this vector, this has a representation B11, B12, B22, B21, B22. Now, the thing is that there must be the combined transformation. B, A followed by B, A followed by B is a transformation that does what? So that acts B11, B12, B22, B22 on A11x plus A12y, A21x plus A22y, and again, but this is now a two by two matrix acting on a column vector. So what this will give is equal to, you have to B11 times A11x plus A12y plus B12 A11x, sorry, A21x plus A22y, and here you have B22 A11x plus A12y plus B22, this is 21, sorry, B22 A21x plus A22y. So this is the complete transformation now. But this transformation is nothing but, if you just combine this, you will get B11 A11 plus B12 A21 x plus, what is y now? B11 A12 plus B12 A22 y. And similarly here you will get B21 A11 plus B22 A21x and finally the last bit is B21 A12 plus B22 A22 y. But this is nothing but, therefore, that you have a matrix. So if you combine, basically what we are saying, if you combine this matrix A11, A12, A21, A22 and act on that by, on the left, B11, B12, B21, B22, then we get the vector which is B11, A11 plus B12, A21, B11, A12 plus B12, A22, and here we have got B21, A11 plus B22, A21, and B21, A12 plus B22, A2. So you see, to make sure that the, let's write down again, B, A followed by B. And then the effect is you go directly as a multiplication of BA, and in such a way that the matrix element for this is nothing but Bij A Kj summation over K. So the rule for matrix multiplication is the way it is so that the composition of two transformation is another, so I should say linear transformations is another linear transformation. So we say that C equal to BA, and let's say we say that B11, B12, B22, B2, I'm sorry, B21, B22, multiplying with A11, A12, A21, A22 is equal to get this element, you multiply. So we'll just use the several colors. So this times this is here. So let's write down. This is B11, A11 plus B12, A21. Similarly, now next color. Similarly, this plus this, I'm sorry, and this gives you this element, which is B11, A12 plus B12, A22. Similarly, two more left. You have this and this. So that gives rise to here. And you can read off B21, A11 plus B22, A21. And lastly, you have this, and this is the last element here. So let's just do that. B21, A12 plus B22, A. So one way of writing this down is Cij equal to sum over Dikakj. K is equal to 1 to 2. So let's understand this. Suppose I put C11, I equal to 1, J equal to 1. That's equal to summation K equal to 1 times 2 B 1K A K1. And see, this is nothing B11 A11 plus B12 A21. This is exactly this element. Okay. Bottom line, multiplication. Bottom line, a matrix represents a transformation of a vector into another. Linear transformation. Multiplication of matrix is applying the transformations one after another. Thank you, and we'll meet again.